Okay, so we have spent a lot of time talking about substitution. In this video, I want to cover elimination reactions, which are somewhat of a competing reaction. Like I discussed in class, um, when you're thinking about elimination, you basically need a base. So one thing that distinguishes a substitution from an elimination reaction is that, for example, you have the hydroxide that is going to behave as a nucleophile, and what that means is that it should be able to get to the site of action and it should be able to donate its electrons so that the leaving group leaves. Of course, in this case, we haven't really specified what these groups are depending on whether they're H's or whether they're methyls. You can predict whether it's going to be SN1 or SN2 process, but in this case, realize that you will take advantage of the ability of the nucleophile to donate electrons. So nucleophiles are great Lewis bases. And the second reaction that I have over here, which is an elimination reaction, in that case, we don't take advantage of the nucleophilicity, but rather the basicity. And when you're thinking about any atom or group of atoms which are basic in nature, you should think about abstraction of protons. That means removal of protons. So what you're saying now is that the hydroxide is going to cause abstraction of the beta hydrogens. Electrons will kick in, Br will leave, and you will end up with a alkene. We talked about this reaction in good detail in both chapters 7 and 8 when we talked about alkenes, method of preparation for alkenes. If you have an alkyl halide, we ran that reaction in the lab, going from a tertiary alcohol into the corresponding alkene in presence of an acid. And of course, we also discussed that at good length when we discussed alkyne. So it's the exact same reaction that we are referring to, but now we are going to take a look at the two kinds of elimination, the E1 and E2, which derive their nomenclature pattern pretty much following the SN1, SN2. So it's very, very similar to SN1 and SN2 with just one additional parameter, which is what I'm going to talk about in the next 15-20 minutes or so. Now, when we think about elimination, we've learned before that the alkenes that you get, the most stable alkenes are the ones that are also most substituted. So, for example, you have over here 2-bromobutane, which can be drawn as that. So you have the option that the two hydrogens that are beta, so this is alpha, that's beta, either these two hydrogens can be lost or the three hydrogens on the other side, they may be lost. So you have the potential that you could get an alkene like that or an alkene like this. And since the first one is more substituted, when I use the word substituted, again, it basically means that you have more number of alkyl groups on that double bond, and that would make it more stable. And as you can see, we have 81%, so your major product is also the more substituted alkene. When you take a look at the second case, which is the case of a tertiary halide, it's the same story or similar story. So that's one alkene. And this is another alkene. And again, the major product is your more substituted alkene in this particular case. But the reaction mechanism that we see in both of these is going to be different. And like I said, that's what we are going to discuss in the next couple minutes. Now, E1 derives its name essentially from the same as SN1. So SN1 was nucleophilic substitution, which was unimolecular. E1 is going to be elimination, which is unimolecular. So unimolecular elimination. What else can you think about SN1? Hopefully you recall that it was a two-step process. and it required, like energy-wise, the valley that you see between the two humps, that basically gives you an intermediate. And it was specifically for tertiary halides. And that is exactly what you see in case of E1 as well. This is going to be an elimination reaction. It will be a two-step process. So the intermediate is going to be a carbocation, but you will see that in case of tertiary halides and tertiary halides alone. The basic difference between SN1 versus E1 is that in case of SN1, you would be thinking about a nucleophile. In case of an E1, you're thinking about the basic character. So you're no longer worried about the Lewis basicity or the ability of that Lewis base to be able to donate electrons, but rather the ability of that base to abstract a proton. So whether or not it can abstract a proton, that's what we are going to focus on. So abstraction of proton means it's going to accept a proton, so it now becomes a Bronsted base, not a Lewis base. So recall the three things that I told you in class, and I also put them in the little cheat sheet that I developed for the substitution reactions. When is it substitution? When is it SN1? And when is it SN2? And it's under content still. And I also sent an email about it, so you can take a look at that. Recall in that I talked about three things. One was you should have a negative charge. That is the first and foremost. The second is that it should be small in size, small enough that it can run to the site of action. The site of action would be a carbocation usually, and be able to donate the electrons. So if you have it too bulky, that bulkiness is going to prevent its movement, and so you would say that that's not a good nucleophile, but rather a poor nucleophile, but it could be a base. So you have to consider both of those when you are predicting whether a reaction is going to go through an SN1 or an E1 reaction. E2, which is similar to SN2, is a concerted reaction. That means in this case, you're going to see the transfer of a proton and the loss of the leaving group, both synchronized in one single step. So it's a single step reaction. That's the easiest to remember. So you can perhaps see that both SN2 as well as E2 are concerted reactions. They occur in single step. Their energy profile looks like that. Energy on the y-axis, of course, the reaction progress on the x-axis. E1, on the other hand, is very similar to SN1, goes through the carbocation, two-step process, unimolecular, of course, and the carbocation will have to be formed. So tertiary systems will have competing SN1 and E1 reactions, whereas primary systems would usually have an SN2 or E2 type of a reaction mechanism. And so now we have to basically distinguish when do we see substitution, when do we see elimination, how do we distinguish the two from each other. Okay, mainly there are two things that you would be focusing on when you are looking at substitution versus elimination. Like I said in class, substitution means you need a nucleophile. Elimination means you need a base. So what makes a good nucleophile? A good nucleophile should be able to donate electrons and should be small enough a base also is supposed to, and this should have a negative charge, of course. A base is also supposed to have a negative charge. But while nucleophiles are small, bases can be bulky. So things such as T-butoxide, for instance, which cannot run to the site of action and is a poor nucleophile, is actually a great base. And so it would rather abstract a proton, and hence if you have T-butoxide written, potassium T-butoxide written on the arrow, it always will go through elimination. Elimination. Always. Okay. The other thing that we will use to distinguish between the substitution and the elimination reaction is the temperature. Elimination reactions are supported by high temperatures. High temperatures. And when I use the word high, meaning 50 degrees or higher, I mean high is really a relative term, but usually you would see like a specific number or like the triangle drawn for heat. So they are kind of taking their time to go out of their way to tell you that we are subjecting that to heat, and that will go through an elimination reaction. So high temperatures facilitate, they allow elimination. Substitution, usually room temperature or low temperatures, that is when you would see that. That does not mean that it always has to occur only at room temperatures, but that's the general trend, that elimination does require high temperature. So again, to reiterate, nucleophiles have to quickly go to the site of action and be able to attack. So you will usually associate the word fast or fast reaction with a nucleophile. And so one can, envision that this is kind of like a kinetic product. On the other hand, if you're thinking about um, if you're thinking about a base does not really reflect how quickly the equilibrium is established, and so it doesn't matter because you're not really measuring the speed of the reaction, and you're only measuring the stability and the position of the equilibrium. So basicity measures that stability, and hence you're looking more in the thermodynamic aspect of the reaction. On the other hand, a nucleophile, because it's the speed of the reaction that we are looking at, the key thing there to look for is the kinetics of the reaction. Now, when you're comparing the elimination versus the substitution reaction, you should keep in mind that both E1 and SN1 will require the formation of the carbocation, and so those are the two-step processes. But the way we distinguish between SN2 and E2, it's slightly different. You do expect it to be a single step process, but the substrate dependency is not exactly true. Recall, we said in SN2 reactions that SN2 reactions go through only the primary. That means if you have like a tertiary alkyl halide or an alcohol, as the case may be, let's say it's an alkyl halide. We said that SN2 is not going to take place because of steric reasons. Steric reasons. Because the nucleophile essentially will not be able to see the point of attack. On the other hand, if you have to carry out, like an elimination reaction where the bromine has to leave and one of these hydrogens has to go away as well, so that you get isobutene, that reaction can take place in an E2 type of a format also. So both E1 and E2 are possible in that case, because now you're not taking advantage of the nucleophilic character, you're rather taking advantage of the basic character. And so sometimes you would see that the tertiary substrates, they react even more rapidly as compared to the primary substrates. So realize the subtle difference between the kind of substrates. E2 will require, mechanistically, it will require a specific type of geometry, and that geometry is what is called as anti-periplanar. And what I mean by that is the following. If the leaving group and the proton that is supposed to be lost, if they are absolutely anti with respect to each other, so recall what you learned in chapter 4, rather 3, if your leaving group, I'm going to just call that Lg, and the hydrogen, which is supposed to be at the beta carbon. So this is beta, and this little dot here is alpha. If these two are absolutely anti with respect to each other, you would say E2 reaction mechanism is possible. It's feasible. On the other hand, if it's not, so if your hydrogen is at another location, or it is gauche or askew, not anti, then you're not going to see E2, and in that case we will have to see if the reaction conditions are going to favor E1, and then in such a case an E1 reaction mechanism will be possible. So realize what's happening. Realize that one more time. What's happening is that you have a leaving group here. The leaving group that you have is X. This is your leaving group. And hydrogen is going to be pulled off with a base. And so the base is basically abstracting your beta hydrogen, and X is leaving, and both of those, they are occurring, both of those steps, they are occurring together at the same time, not as two separate steps, and so they are concerted really, they are orchestrated really well. So your transition state looks like your leaving group wants to leave, and the bonds between the carbon and the hydrogen, they want to form the pi bond. Like I said, X wants to leave. You have two groups, R1, R2 perhaps. And so the base is basically picking up that proton, and the electrons are going to move in between the two carbons, and the X is going to leave as well. Your end product is going to be the alkene, the BH with a positive charge, and X minus would have left. And again, if the leaving group and the hydrogen are absolutely anti with respect to each other, that means they are at a difference of 180-degree dihedral angle, you would call this an E2 geometry, or rather E2 elimination, which follows the APP, anti-periplanar geometry is required for this process to take place. Now one might ask, well, what's wrong with when it is thin? Realize, if it is thin, that means both the H and the X are pointing in the same direction. This is what your Newman will look like. This is what your Fisher will look like. Notice how close they are. They're eclipsing. So now, since they're eclipsing, they will have steric interactions. So if the base comes in from here, in your transition state, lots of bulk is on one face of the molecule. And for those steric reasons, I've said that before, usually you would see only two factors which decide the outcome of the product. If it's not the electronics, it's got to be the sterics. And so in this case, because you have for the steric reasons, for the steric interactions, the thin periplanar geometry is going to be a high energy state, and that will not be allowed in case of an E2. So it has to look for the anti-periplanar again. Only then and only then the reaction will take place. So I'm going to take the time to go over some problems, some examples, so we can see what we mean by this, and apply it. So notice orbital-wise, you can perhaps envision that the anti-periplanar reactant X wants to leave. Hydrogen will be picked up by the base, and then the lobe over here and the electrons from here are going to form essentially the p orbital overlap to get your alkene product. So E2 requires anti-periplanar geometry. SN2 via a backside attack. So there is specific stereochemistry that is required in both of these reactions, and that's a common theme between the two. So since E2 is a stereospecific reaction, hopefully you can see over here that the leaving group bromine and the hydrogen, notice they are completely anti with respect to each other. So the reaction can go through an E2 reaction mechanism, and the product that you're going to get at the end of the day would be, in this case, you have both the phenols pointing in one direction. So if you had to assign, you would say high priority for the bromine and high priority for the phenol. So those are the final product that you end up with is an E configurational isomer. But again, realize for the reaction to be E2, the base that we utilized was KOH, which was a strong base. The reaction will have to go through essentially an anti-periplanar reaction mechanism. All right, so let's take a look in terms of some other examples using maybe chair conformations and boat conformations. Let's talk about these three examples. So I have a chair conformation, I have a Cl, which is a leaving group, of course, and I have on the next carbon there's a methyl over here, there's an isopropyl group over here, and I'm subjecting that to E2 conditions. And we'll discuss in a little bit how do we distinguish between the E2 versus the E1 reaction conditions. But for now, focus at the APP. What does that mean? Your Cl is the leaving group, so that wants to leave, but at the same time, you want a hydrogen which is anti with respect to this leaving group. So one is if you view from here, your Cl is pointing downwards. That means you need exactly opposite to that. You want a hydrogen. Is there one? The answer is no. So would there be a reaction? The answer is no. On the other hand, if you see on the other side, so you have to view, through this bond, again, Cl is pointing downwards and you have methyl on top. What happens there? Basically, you do not have the same picture again, and so you're going to, again, not be able to visualize the APP, and so in this case, no reaction takes place if you have E2 conditions. So what can be done? Well, nothing. You either run the reaction in E1, or if the reaction allows for a substitution reaction, maybe a substitution will take place, but E2 reaction condition is not going to be allowed. Let's take a look at again an E2 reaction. So I'm seeking APP, anti-periplanar, for the reasons I just discussed. You have Cl pointing downwards, and if you look through the bond, you're supposed to have a hydrogen, but guess what? You have a methyl over there, so the reaction is not going to take place in that direction. But if you notice, you do have something on the other side. You do have a hydrogen which is axial and another hydrogen which is equatorial. And that axial hydrogen is going to be completely anti with respect to the Cl. So when the base comes in, it's going to pull off that proton, electrons move, Cl leaves, and you end up with a methyl. And on the adjacent carbon, you're going to see a double bond. So you can, of course, show that as a chair as well. Take a look at the third example. You have Cl and methyl which are trans with respect to each other. You have Cl and methyl which are trans with respect to each other. That means at any given point of time, if you wanted to convert it into, you don't have to, but if you wanted to convert, you can say Cl is pointing downwards, methyl and methyl. Can this go through E2? The answer to that is no. So no reaction takes place here as well because the methyl groups are blocking that anti-periplanar position. So since there is no hydrogen over there, the reaction cannot go through. Okay, let's take an arbitrary example. I have, let's say, 2-bromopentane, and I'm treating that with sodium methoxide in presence of methanol, and I'm warming it up. So I'm expecting elimination, and I have essentially two products that are possible. These are the two products, and the first one, like we discussed, is the more substituted, is also called as the Zaitsev product. The second one, which is less substituted and is your minor product, is also referred to as your Hoffman product. Now, realize that sometimes small changes within the reaction can actually bring about a big change in terms of your product. What do I mean by that? If you use a small base, such as sodium methoxide, like an alkoxide, essentially you're going to end up seeing more of the Zaitsev product, less of the Hoffman product. On the other hand, if you change your reaction conditions and perhaps you change from methoxide to T-butoxide, which is a more bulky group, the effects of this change basically have very magnanimous changes in case of your product, and you're going to see much more amount of the Hoffman product because of steric reasons. So what I just said is that if you treat this with a T-butoxide, which is a sterically hindered base, sterically hindered base, you're going to end up seeing more of the Hoffman, so that becomes your major, and Zaitsev's will become your minor product. It probably is also worth to mention here that Hoffman elimination is favored by certain leaving groups. Typically, if your leaving group is a fluoride or if it is an onium ion, that means not a, something like let's say ammonium NH3 with a positive, or a hydronium, that's a possibility, or sulfonium. Those will be great examples for carrying out a Hoffman elimination product, provided the correct bases are given. So usually one can say, to be on the safe side, one can say ammonium specifically, and then F negative. If those are your leaving groups, it's going to go through a Hoffman elimination rather than the Zaitsev's elimination. So just keep that in mind as an exception. Another thing that can be said is that if you have a sterically hindered base, like a T-butoxide, for example, then the probability that you could see a good amount of Hoffman product is pretty high because a sterically hindered base is used. So one can say that the regiochemical outcome of an E2 reaction essentially is, or can be, controlled by carefully selecting the base. So let's say I have a starting material. I'm treating that with ethoxide, sodium ethoxide, of course. And you have to figure out the product when this is treated under E2 conditions. So you have a strong base. So hopefully you can identify that strong bases facilitate E2 reaction mechanism. You have to provide the product. So now if you think about how to go about it, the first and foremost thing that should come to your mind is that the kind of base that you have used is it is strong, but it is not hindered. Strong but not hindered. So in terms of where the double bond would form, you can hopefully see that the double bond should form over here because of that reason. Now, if you consider the stereochemical outcome for that, that basically should tell you that you are looking at the beta position. So this is Cl, that's alpha. The next one over is beta, and you have the methyl group, and you have the hydrogen pointing backwards. So if you expect, since you expect this reaction to be stereospecific, essentially you can expect that only you can expect only one alkene rather than mixture of stereoisomeric alkenes in this case. And so if you view the molecule, sort of through this bond in order to get your correct stereochemistry, you would say that your hydrogen is pointing maybe on the left hand side, methyl is pointing to the right, ethyl is pointing downwards, and then you have your second carbon, which is your alpha. So in this case, this is beta and this is alpha. And you can perhaps view that the Cl is going to be on this side, methyl on top, hydrogen on this side. So now you're seeing you need to draw the conformation in which the hydrogen on the front carbon and the leaving group, which is on the back carbon, and they must be anti-periplanar. That means you need to rotate, essentially. So as you rotate that, you're going to get, let's rotate it by 60 degrees. So you'll get an ethyl, you'll get a hydrogen, this one is a methyl, and on the back carbon you have, of course, the methyl still where it is, the hydrogen, and the Cl. So now you can see that your two groups, the Cl and the H, they are anti-periplanar to each other. So your E2 reaction can take place. What does that mean? That means that as Cl leaves and hydrogen is going to donate its electron pair to the carbon-carbon bond. That means that the ethyl and the methyl should be on the same side, and the methyl and the hydrogen should be on the same side. So one can draw maybe the double bond. You have the ethyl and the methyl on the same side, and you have the hydrogen and the methyl like that. And so this, in this case, is going to be your Zaitsev's product, because it will look like, oh, one extra carbon. Let's get rid of that. So 1, 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. And here is your other methyl group. And that's your product. Now, let's talk about the E1 mechanism. Now, E1 mechanism has two separate processes. The leaving group leaves, Lg leaves. That's the first thing. And it gives you the carbocation intermediate, and that then loses a proton in a separate step, and it gives you your alkene. So you can show that as leaving group leaves. You get your carbocation, you have the hydrogen, the base picks up the hydrogen, electrons move, you end up with the double bond. So the first step, which is the loss of the leaving group, is your RDS, your rate determining step, very similar to the SN1 process, though the base does not participate in this step, and so the concentration of the base doesn't really affect the rate of the reaction. And so because of this step, because it involves only one chemical entity, we call this unimolecular. So one can say that the E1 stands for unimolecular, much the same way as the SN1 stands for unimolecular. So that kind of goes hand in hand. So you can perhaps envision that E1 reaction will generally be accompanied by a competing SN1 reaction, and so in general a mixture of products will be obtained. And after this discussion, I'll probably pick up one or two examples to kind of show you the that effect. So let's take a look. Let's consider the effect of the substrate on the rate of the E1 process, since the rate is sensitive to the nature, and you know that tertiary halides react more readily towards like formation of a carbocation than the secondary halides or the primary. The secondary and the primary will in general not undergo E1 reaction mechanism. So this is similar to the trend that you saw in case of SN1 tertiary are the ones that will go through E1, but tertiary can also go through E2 in that case for the reasons we discussed early on. So both are possible. Now, in terms of leaving group capability, if you have something like, like an alcohol, it's a bad leaving group. You have to treat it with an acid so that you generate a good leaving group, and that is then ready to leave. So as it leaves, it will give you, after the reaction with the conjugate base, it will give you the corresponding alkene. And usually it will be the Zaitsev product that you're going to see. But nevertheless, just be aware of what I told you about the Hoffman product as well. Now, it's important to realize that because substitution and elimination reactions are competing reactions, it is not necessarily true that you're going to have only one clear product. I mean, sometimes you would, but sometimes you won't. So let's say you're given that you have this dibutyl bromide, which upon treatment with OH negative gives you one clear winner. Your product is an E2, follows an E2 mechanism, is the one that is followed to get the product, and that's the only product that you obtain. Now, the way you should approach this problem, if you have to explain this, is, well, why is it that E2 wins this competition? So if you think about SN2, what are your other possibilities? SN2 is a possibility, SN1 is a possibility, and E1 is a possibility. SN2 is not going to take place because this is a tertiary halide. And sterically, it's very demanding for the nucleophile to get to the site of action. So steric hindrance is going to prevent SN2 from occurring. Now, if you consider unimolecular processes, in that case, you have to generate a carbocation, only then the reaction is going to go forward. What that means is that you have to see the Br has to get converted into the carbocation. And recall what we learned about that. That is your rate determining step. That means it's a very slow step. So if the rate of the reaction of the elimination in an E2 manner is going to be faster as compared to the RDS, then of course the SN1 and the E1 cannot compete. On the other hand, if that is faster, then it's basically the one that's the fastest is going to that's going to take place. So you have to kind of keep think about all the possibilities, and then take off the ones that you're not going to see as much. So again, it's the rate determining step for E1 or SN1, which is a super slow step, and therefore they would only win the competition if the competing E2 is extremely slow. And when would the competing E2 would be slow? It would be slow if this reaction was done in presence of a weak base, such as, let's say, water. So if you use a weak base, then you are going to see a competing reaction that you will see both the reaction in a substitution sense as well as the elimination. On the other hand, if you have just a strong base, you're going to see the reaction mechanism go via an E2 in this case. So if you're asked what are the major products, be aware that substitution and elimination kind of go hand in hand. They're competing reactions, and then basically see if there's only one product that is getting generated, what could be the possible reason that the others won't get generated. That's an important point to make. So if you had to kind of put things in perspective and now have to see about, how do you decide what is a nucleophile, what's a bad nucleophile, what's a good base, what's a weak base, that kind of thing. So things which are nucleophilic only, usually among halides, you could say that chlorides, bromides, iodides, those are mainly nucleophilic. Likewise, if you think about SH negative, that's a great nucleophile. RS negative, that's a great nucleophile as well. H2S, RSH, these are all nucleophilic in nature. If you think about things that will have only basic character, if you have a hydride or if you have a T-butoxide, those are base only. And the reason for that is, in case of the T-butoxide, you have a very bulky structure, so it's the bulkiness. And in case of H negative, the size is so small that the negative charge cannot quite be given as a nucleophile. Does not mean that it never behaves, but usually it will have a basic character. What is both nucleophilic as well as basic? So these are the tricky ones. So you have the hydroxide, you have the methoxide, you have the ethoxide. These can behave both as nucleophile as well as a base. And if you're considering a weak nucleophile or weak base, usually the protonated versions, so water, methanol, ethanol, these will be considered poor nucleophiles, and since they're poor nucleophile, they also will support SN1 type of a reaction mechanism. So let's say you were given 2-bromobutane and that is being treated with a hydroxide. Now that hydroxide is a nucleophile and a base, so you should expect that this should give you both substitution as well as elimination. And since this is a strong base, you will expect this to go through an E2 reaction mechanism, and SN2, because this is secondary, and usually will require, like DMSO type solvents perhaps. And so your product is going to look like, because it's hydroxide, you will say that it's going to be the Zaitsev's elimination. You will need to warm it up in that case, even if it's at room temperature. That will be considered relatively warm, and it will also give you an SN2 product. So if, let's say, you had stereochemistry over here, you're going to end up with an inversion of configuration in this case. But you will see elimination and substitution, both of those in this reaction mix. So if you have the reaction that's given to you, it's a tertiary alkyl halide, and you're treating that with water and ethanol. So water, that tells you that it's a poor base, and it's or a weak base, however you want to call that, and it's also a weak nucleophile. So you are going to see essentially both of those possibilities, that the substitution and the elimination will take place. And that's what you're seeing. You have the substitution and you have the elimination that takes place in this particular case. And whether the reaction takes place via an E1 or an E2 reaction mechanism really depends on the speed of the reaction. And in this case, this one should be an E1. since water is a weak base, it's going to facilitate an E1 reaction mechanism. That means the carbocation will be formed. On the other hand, if you would have used a hydroxide, then an E2 would be favored over that. So hopefully you can see strong bases, just like strong nucleophiles, strong bases, they allow E2 reaction mechanism, which follows the APP. On the other hand, weak bases, they allow for E1 reaction mechanism. It's going to go through the carbocation formation. So E2 reaction conditions will be sometimes also referred to as strong concentrations, so higher concentration, strong concentration of the base, So notice your leaving group is right over here, and here is your hydrogen. So if you have like a molar solution of ethoxide, which is a strong base, then you're seeking E2 elimination. The double bond ended up being in between here. It did not affect the isopropyl group. On the other hand, if you want the reaction to go through E1 elimination, then this molecule will have to go through a ring flip so that you can get a carbocation, and you no longer have to worry about getting the APP geometry. And in that case, you're going to see a double bond which will show up essentially at this location, or the more stable tri-substituted alkene. So E1 requires formation of a double bond, and the APP geometry doesn't have to be followed. E2, on the other hand, is very stereospecific, and that's what we look for in an APP geometry. All right, sometimes you might see what is called as E1 conjugate base reaction, which is slightly different than the traditional elimination reactions that we have been talking about. An elimination reactions like a regular E1 requires a carbocation formation. Like I told you in class, the alcohol forms the positive charge, OH in presence of, let's say, H2SO4. That gives you the OH2, the water leaves behind a carbocation, and that is what then loses the proton. In this particular case, your transition state, or your intermediate rather, is not going to be a carbocation but rather a carbanion. So this is seen when you have like electron withdrawing groups connected to the beta hydrogen. So in that case, what can happen is resonance in between, and hence a shift of or loss of proton becomes easier. Maybe that's a better way to say that. And so since oxygen pulls electrons towards itself, that makes this hydrogen very acidic and generates a negative charge, and there is resonance now in between the negative charge and the C double bond O. So as the electrons move, they facilitate the loss of the leaving group, generating the alpha beta unsaturated ketone. So this is kind of like a rare event, but it is possible if your beta carbon is connected to anything that's electron withdrawal. So, long story short, if you had to predict, let's say you were given a bromine at the benzylic position that's being treated with formic acid and water, notice protic solvents, poor nucleophiles, or weaker nucleophiles, but then you also have benzylic position, so you can actually show the loss of that proton or loss of that bromine, so that you generate a carbocation, and so whatever has to happen will go through an SN1E1 type of a reaction mechanism, and so your two products that are possible are shown. So again, realize substitution and elimination are competing reactions. We talked about strength of the base, and that decides E1 or E2. So stronger is the base or high concentration of the base, that means E2. Weaker base or poor base, that means E1. You will usually see temperature written on the arrow to kind of have majority of it as an elimination reaction. If it's not written, then maybe majority of it is going to be the substitution product. What else? In case of substitution, again, you pay attention to what's on the what's the substrate. If it's a tertiary, then you seek SN1. If it's primary, you seek SN2. Secondary, it's in between, so you pay attention to what's on the arrow. Good nucleophile, SN2. Poor nucleophile, SN1. Polar solvent, SN1. Polar aprotic solvent, SN2. Both of those do require good leaving groups. However, if it has to be a substitution, it is kind of contingent upon the loss of that leaving group. So sooner or later that has to leave. And if you don't have a good leaving group, just say no reaction. So for instance, if you have something like an NH2, which is a leaving group, I talked about that in class. That's a really bad leaving group, and so the reaction is not going to cut it. That's not a good reaction. I think that's it as far as the elimination goes. But like I said, we should expect the substitution and elimination to go hand in hand. If the question expects you to provide all products, then you should just provide all substitution as well as elimination products. All right.